first presentation, and we'll give you time to set up. It's called the Water Quality Model of the Almendares River Watershed in Cuba. It's by the University of Miami students, Jeff Iudicello, Dylan Batterman, Matt Pollard, and Cameron Scheid. I will let each of the students some time to set up and to introduce themselves. The presenting team may sit here.
Let's go. Good morning. My name is Jeff Iudicello, and I'd like to introduce my teammates again, Dylan Batterman, Matt Pollard, and Cameron Scheid. We're students at the University of Miami, and our project is called Water Quality in the Almendares River Watershed, Havana, Cuba. Okay, some project objectives. First of all, to develop a water quality model for the Almendares River, we'll be referring to that model as the model, okay? The goal is to link non-point sources and land use with in-stream concentrations in the Almendares River. The second objective is to identify critical locations in the Almendares River watershed that are likely to have the worst water quality. This is important and it can help reduce risk to human and environmental health by identifying the most concerning areas. The third objective is to provide a basis for future water quality modeling and analysis in Cuba. This model is especially useful in areas with little or no available data, as we found out in Havana, and I'm sure many of other regions of Cuba are the same way. Okay. The Almendares River watershed contains most of the city of Havana. As we all know, Havana is a coastal city on the north coast of Cuba. The Almendares River originates in the southern portion of the watershed down here and flows northerly to its outfall into the Gulf of Mexico. The Almendares River is 30 miles long and has a watershed area covering of about 154 square miles. Okay? Just a few statistics. 53% of the Almendares watershed is in the city of Havana. The remaining portion of the watershed is in the south here, south and east of the city. Most of that land is agricultural or non-developed, although there are pockets of urban areas in that southern portion. 47% of the drinking water comes from groundwater in the Almendares watershed. Okay. Here are some images of the river. You can see in the upstream areas that the river is relatively shallow and narrow, whereas in downstream areas the river is noticeably wider and at least deep enough for some small boat traffic. This is an example here of a direct drainage discharge from a pipe, and it's fair to assume that these kinds of connections are very common in the watershed. So the current state. The river receives unregulated waste from residential and agricultural sources. There have been reported water quality problems, such as high metals content in the river and excessive in-stream concentrations of nutrients and bacteria. These problems are normally associated with non-point source pollution. Metals normally are indicative of urban areas, whereas nutrients and bacteria are indicative of agricultural or undeveloped areas. And the big concept is that the risk to human health is significant when there's serious water quality problems. So at this point, I'm going to give the floor over to Cameron. He's going to talk about the delineation of the subwatersheds.
Hi, everyone. All right, to begin, all maps and delineations were done within ArcGIS using the most recent data sets and satellite images we could find. And what that did was create a spatial and coordinate reference frame for us to take area and length measurements within the program. So this first map here is our Almendares River watershed map. The boundary is shown in yellow and was determined based on available elevation data. As you can see here, for instance, the Havana Bay is not included in the watershed because of a ridgeline that lies along this boundary. And just as a point of reference for the rest of the presentation, when we refer to upper and lower regions, we're referring to regions upstream of the reservoir to the east and the regions downstream in the lower portion of the reservoir to the north and the west. This is our land use map, which is where we got our area values from. The urban areas shown in white represent developed lands for commercial, residential, and industrial purposes, whereas the green represent the non-urban lands or undeveloped areas, pastures, farmlands, or areas where row crops could clearly be seen from the satellite image we were using. And you can see the density of urban areas to the northeast, whereas or to the northwest, whereas the non-urban's most dense in the southeast. This is our final subwatershed delineation. Each individual subwatershed was defined by intersecting the contributing area of neighboring rivers and streams. And there ended up being 62 subwatersheds, 22 in the upper region, and 40 in the lower. Now I'm going to hand the floor over to Dylan, who's going to talk about hydrologic data.
As you may know, there is little hydrologic data available for Havana. So we had to expand our geographic view and consider using data from other areas, notably South Florida. Here we have the region of study. As you can see, Miami and Havana are geographically close. Therefore, we checked the similarities of the rainfall and climate data of South Florida with that of Havana for application in our model. Also note here that the South Florida rainfall station area is shown, which I will get to in a later slide. This is the meteorological comparison for Miami and Havana. As you can see, the average temperature is very close at 24 and 25 degrees Celsius. And the annual number of wet days is also within 10 years being very close as well. The relative humidity and wind speed are also pretty similar. So as you can see, the two cities have similar climates. More importantly, here we have the average monthly rainfall comparison of Miami and Havana. And note the bimodal trend, which is very unique to the two cities. 5 South Florida hourly precipitation sites were used to determine the data to be used in our model. The 5 sites include Boca, Homestead, Miami, St. Lucie, and West Palm Beach. And here we compare the average annual rainfall of the 5 stations with that of Havana, and as you can see, Havana falls within the range. These are the calculations that were used for the estimation of runoff coefficient C. By definition, C equals the annual runoff over the annual rainfall. And using South Florida data, curve number was determined as a function of curve number and directly connected impervious area. Curve number is a parameter that is used for predicting direct runoff based on hydrologic soil group or based on the permeability of the soil. And directly connected impervious area, however, refers to land use. More specifically, directly connected impervious areas are those areas that are hydraulically connected to a conveyance system and thence to the outlet points and without flowing over pervious areas. The DCIA percentage used refers to the percent of the land area being studied that is DCIA. These are the tables that were developed in a study that will use the meteorological characteristics of South Florida to determine runoff coefficient as a function of curve number and directly connected impervious area. And while we did not know an exact value for curve number or DCIA, we came up with what we thought were the most reasonable values as shown here and used them to determine runoff coefficient. And the strength of this approach is that we did not assume any particular value for curve number or for DCIA, but rather we used a range of values and used them to determine runoff coefficient. Realizing this, that we did not have an exact value for runoff coefficient, we took a mean of these and used them to determine the value. Now I'm going to introduce Matt, who's going to talk about water quality parameters.
Thank you. So the motif of this project was the absence of data where we really needed it. So the biggest questions for water quality parameters were what parameters are we analyzing for, what sources are we using, and how are we validating those sources as an accurate estimate. These are the parameters that we analyzed for. Total nitrogen, total phosphorus, and fecal coliform are 3 of the most important parameters in water quality. TN and TP analyze the nutrient level. That's very important for bacterial growth. And fecal coliform is a more direct measurement of bacteria. We also have BOD 5-day up there. That's a measure of the organics in the water. And we also have several heavy metals. Lead has an asterisk because that's the example that we'll be using for the remainder of the presentation. So then the next question became, what model are we using to analyze the concentration in the runoff? In this case, we used EMC, event mean concentration. That's the most common method used. And EMC mathematically is the mass of pollutant in the runoff per the volume flow of the runoff. And we analyzed this for the urban and non-urban areas separately. The next issue became, what sources are we using and how do we validate them? Most of our sources came from South Florida, with the exception of one that came from Kingston Harbor, which is in Jamaica. And in all of these models, we had a natural water body moving through urban and non-urban areas and ideally outlet to the ocean. The source we used to validate this for was an EPA report, which is sort of the Old Testament, if you will, of EPA concentrations. Here's the graph that we have. The probability distribution we have here represents the EPA model, and then these are individual data points down here that we use to calculate the mean and standard deviations. The next question became, what water quality standards are we using? We use the Florida Department of Environmental Protection water quality standards for the state of Florida. That's the state equivalent of the EPA. And we analyzed it for class 3 water bodies, freshwater, which mostly concentrates on water being fishable and swimmable. Here's a summation of all of the data that we used. We have a mean and standard deviation for the constituents and the land uses that we analyzed and plugged into the model, and then here are the Florida standards. The ones that we do not have numerical values, those are there because the model, the water quality standards, did not have numerical values. And now I'm going to turn the floor over to Jeff, who's going to talk about the model itself.
Okay, this image represents the model formulation. The model is considered essentially at 2 different scales. The first scale is the subwatershed scale. The second scale is the river junction scale, okay? At the subwatershed scale, the total area was divided into urban and non-urban areas. The total outflow and the average concentration at the exit of each subwatershed is a function of the rainfall and then the runoff coefficients and EMCs per land use as described by Matt and Dylan. At the junction scale, the junctions represent the intersections of neighboring subwatersheds, okay? The flow exiting a junction is the summation of all the flows entering into that junction. However, the average concentration at the junction is a flow-weighted average. In cases where there is an upstream subwatershed contributing flow and concentration, this flow was just summed directly here at the junction, and this concentration was attenuated over this distance of the lower subwatershed. I'm not going to go into delve deeply into the mathematics of this. It's all in the report and you've read it. But there are 2 important things to notice on this slide. First of all, attenuation is a mechanism, for example, that reduces in-stream concentrations when pollutants attach to sediment and then settle to the bottom of the river. And the net effect of that is a reduction over the course of a distance traveled in this case. This parameter K is an attenuation factor. We had to assume a value, an educated guess, and later on I will be showing a sensitivity study that validates our assumption of the attenuation parameter. Another output of the model is an uncertainty analysis. All of the mean model predictions made are given with a 90% confidence interval for the mean prediction, okay? Those 90% intervals are based on this variance term here. The key thing to notice is that the variance given at all of the model predictions is a function of this standard deviation and this standard deviation, which come directly from the data that was presented by Matt as far as the mean and standard deviations of the water quality parameters. And then this variance here and this variance here represent the flow. And those come from the hydrologic data that Dylan presented. We felt like this was a strength of the model because, as Dylan and Matt had suggested, we didn't know exactly what these parameters were going to be in Cuba because the data is not there. So we did our best guess to assume appropriate values, and then the uncertainty associated with our assumptions are directly built in to the overall variance that the 90% confident intervals then are calculated from. This is a map of the upper region. The notable dominant feature here is the reservoir, and you'll notice that there are relatively few streams leading into that reservoir. I have here noted Subwatershed 42, which is a relatively small area, and I have here Subwatershed 53, which is a relatively large area. I'll be coming back to talk about those two subwatersheds specifically later on. And then this is an image of the lower reservoir. The main river stem considered by the model starts right here, just below the reservoir at junction 119. And the main stem of the river flows in this path through all these junctions as it goes northward to its outfall at the sea. Okay, the model results. The main model result is a concentration prediction at stream junctions, okay? This provides a relative analysis to identify which junctions are of most concern. The model, as I said, also includes a 90% confidence interval, which is useful in accounting for the uncertainties that we had in our data. And then finally, the Florida Class 3 water quality standards are used as a reference or as a benchmark. This is an example of the model output, okay? These black dots are the mean concentrations at the junctions we considered along the main stem of the river. This is the upper region, this is the lower region, and these are presented nicely as a spatial perspective, as distance from the coast in the lower region, and then distance from the reservoir in kilometers in the upper region. The main thing to be noted here is that in both cases, in the upper region and in the lower region, the junctions that had the highest concentrations, in other words, the junctions predicted to have the most probably dangerous or junctions of concern are in upstream areas farther from the coastline and the reservoir, okay? The other noticeable thing is that, again, just using a benchmark as an example for a Florida water quality standard, all of these three junctions in the upper region all violated that water quality standard. And the lower junctions and the downstream junctions in the lower region did not violate the water quality standard, while the junctions in upper regions did. It's also important to notice here that the EMCs used for lead, the magnitudes of these is very similar to what the model predicted as the junction concentration in upstream. That's because it's a flow-weighted concentration and less dilution occurs in upper areas. Again, these three junctions here in the lower region correspond to these three. So it shows you that these are the farthest, most upstream junctions that cause the greatest pollutant concerns. The best and possibly the only way to then remediate these concentrations is to change the input EMCs to what the actual water quality standard is. Doing that, wrong button. Doing that, as you see here, reduces the magnitude of all the predictions, and then, also results in zero water quality violations. I had mentioned earlier that there was an assumption about the attenuation factor. And this is just a sensitivity study to show that using different values of the attenuation factor still produces the same shape and still produces the same junctions of concern. So that validates our assumption. We also compared our model with an established USGS model. I had said earlier Subwatershed 42 is small and 53 is big. You can see here in the smaller watershed, the models predicted almost identical loads, whereas in the larger one, the USGS model was much larger. That's because the USGS model is more dependent on land area than our model is. And just to get into some summary, the runoff model was developed specifically for the Almendares River watershed in Cuba. Non-point sources were linked with in-stream concentrations, depending on urban and non-urban areas. Hydrologic and water quality data was taken from South Florida, and model uncertainty was built into that. We provide a relative assessment of which junctions are most likely to be of concern. And then some conclusions. The junctions of concern are in upstream areas. Dilution and attenuation help reduce downstream concentrations. Remediation efforts should focus on reducing EMCs in upstream areas This is showing that the land use directly affects what the in-stream concentration is. The model is comparable to the USGS model, and our model can be readily adapted to other watersheds in Cuba. This is especially useful in areas with little or no data, like we can assume that most of the rest of Cuba is that way. And it's also ultimately helpful in reducing risk to human health. So thank you.